So consider a cylindrical tube like this, and let's say there is a liquid flowing through it. It can be a liquid or a gas. Okay, so fluids generally. Suppose the cross-sectional area of this tube is capital A and the fluid is flowing through it with a speed V. Okay, or to describe the situation better, let's say fluid is coming out of the pipe with a speed V, right? And let's say the density of the fluid is rho. Now, we are still considering an ideal fluid. Can one of you quickly recollect and tell me the properties of an ideal fluid?
Where it is incompressible.
Incompressible and non-viscous.
Non-
Correct, correct. Ideal fluids are incompressible and non-viscous. So suppose an ideal fluid is flowing through this pipe of cross-sectional area A with a speed V. Density of the fluid is rho. The fluid will have the same density everywhere. Okay. Now, as time passes, liquid will keep flowing out of the pipe. So as liquid flows out of the pipe, we can define something called volume flow rate, the rate at which volume flows out of the pipe. Okay, means how much volume comes out in how much time. That is what we call as volume flow rate. There are two ways of deriving this: volume divided by time. Okay, finite amount of volume by finite amount of time, or small volume divided by the small amount of time it takes to come out. Okay, so in any one of these methods, you can derive the volume flow rate. If you do total volume by total time, you get the average volume flow rate, average rate of flow of volume. If you do dV by dt, okay, you get instantaneous volume flow rate, instantaneous rate at which volume flows out of the tube or the cross section. Okay. Uh, I want you to think carefully and derive expression for this. The fluid is flowing with a speed V, area of cross section is given, density is given. Actually, density is not even needed. I want you both to derive an expression for volume flow rate through that cross section A. You can visualize the cross section also. I am taking the cross section as the end of the tube. Okay. So you can consider a time t or dt, your wish. In that time t or dt, how much volume of liquid comes out? Write an expression for it and divide them. The amount of volume that comes out divided by the time, t or dt, whatever you consider. That will give you the expression for volume flow rate through that cross section. Okay. Do this, both of you. I'll give you 2 minutes. Okay. I got one answer as A multiplied with V. Okay. That is correct. Good. Listen, consider a small amount of time dt. We'll find out the instantaneous volume flow rate. Okay, we'll derive an expression for it. In a small amount of time dt, some liquid will flow out. Okay, visualize the liquid that flows out. Let's say this much volume of liquid flows out of the tube. Or I need not even say out of the tube. I can say flows through the cross section. Okay, fine. I'll shade that volume in yellow. That will be a small volume if the interval is small. So we'll call it as d volume, a small volume that flows out. What we need to derive is that volume divided by the time in which it flows through that cross section. How do you write volume? Volume can be expressed as area of cross section multiplied with the length. Okay. Now we know the speed of flow. If we know speed of flow, then in a small time dt, we can find out the distance that it flows. Speed multiplied with time. Okay. Area of cross section is A. The distance covered by the liquid is V dt. Therefore, the small volume that flows out will be A multiplied with V dt. Okay. That's the volume which flows through a cross section in a small amount of time t dt. Small v stands for speed. Remember that it's not volume. Small v is speed here. divided by the time taken for that part of the liquid to flow out is dt. Cancel this. Therefore, the rate of flow of volume through that cross section is AV. Okay, you can remember this in general. When a fluid flows through a cross section, okay, rate of flow of volume through any cross section is A multiplied with V. But remember, V is the component of velocity perpendicular to the cross section, okay, to the cross sectional area. Makes sense? No, only when the velocity is perpendicular to the area, it will go from liquid will go from one side to the other side. Okay, liquid or gas. If it is moving parallel to the area, it won't cross the area. So it won't count under volume flow rate. It's not flowing through that area. To flow through an area, you need velocity perpendicular to the area. Okay, like in this diagram, you can see the velocity is in the x direction. The cross-sectional area is perpendicular to your screen, means it's in the YZ plane. Okay, is this point clear to both of you? Aishwarya, did you understand?
Yes, sir.
Okay. So now you know how to express the rate at which volume flows through a cross section. Fine. If some volume of fluid flows through a cross section, that means some mass of fluid will flow through that cross section. Now I want you both to write expressions for rate of flow of mass through a cross section. Okay, you make use of the rate of flow of volume. Okay, and based on that, you write rate of flow of mass. And after that, if some mass is flowing out, means if some mass is moving, that means some momentum is being carried by it. Okay, so I want you to write an expression for rate of flow of momentum through the cross section. Actually, momentum is not something which flows, but uh, what I mean is the rate or the amount of uh, momentum carried by the fluid which passes that cross section per unit time. Okay, rate of flow of momentum through a cross section. Do this, both of you. I'll give you 2 minutes. Think carefully. And remember, it is given to you that the density of the fluid is rho. Okay, you can make use of that. In fact, you have to make use of that. I got one answer as rho AV, the other answer is rho AV square. Fine, let's see. First, rate of flow of mass through the cross section. Now we know how much volume flows per unit time. Okay, that is area of cross section multiplied with the speed of flow perpendicular to the cross section. If you know how much volume flows, how will you find out mass? Mass and volume are related by density. Density is mass by volume, so mass becomes density into volume. That's all. So the mass flowing in a given amount of time will be density into volume that flows. So mass per unit time will be density into volume per unit time. So that becomes rho A V. These are some important expressions useful in describing the flow of a fluid. Okay, at what volume, at what speed the fluid is flowing, that is one way you can describe the flow. At what rate the fluid is flowing through a cross section, how much volume is flowing per unit time, you can describe in terms of that. How much mass is flowing in per unit time also will be useful in some cases. So we are just looking at different ways of describing the rate of flow of a fluid. Okay. Next, rate of flow of momentum through a cross section. Now we know how much mass flows per unit time. Okay, dm by dt is rho av. So dm becomes rho av dt. This much mass flows through the cross section in a small time dt. If this much mass is moving, and it with what speed is this mass moving? V. Therefore, the momentum that passes through the cross section in a unit time will be the mass that passes through it multiplied with the speed. This will give you the magnitude of momentum which passes the cross section. So that becomes rho a v square dt. Therefore, the rate of flow of momentum, or we should properly say the rate at which momentum crosses that area, is rho a v square. This is also particularly useful because rate of change of momentum can be related to force. Fine. So this will be useful in describing the force exerted by a moving fluid. I'm not asking you to blindly remember it, but understand how we derived this. So we first derived rate of flow of volume per unit time. Based on that, we got rate of flow of mass per unit time. Based on that, we got rate of flow of momentum per unit time. You can even derive rate of flow of kinetic energy per unit time. How much kinetic energy passes through the cross section per unit time. Not a big deal. You know that kinetic energy is half mv square. So based on that, you can. Okay. One example where this will be useful. Just a moment, I'll show you one picture. Okay. Consider a balloon filled with air. Okay. Let's say its mouth is tied up. Fine. Uh, can one of you describe what will happen if the mouth of the balloon is suddenly opened? Okay, if it is opened freely, what will happen? Aishwarya, you tell me. Suppose it was initially tied up like this. You release it, what happens? Okay,
Sir,
from,
air will
yeah,
get released out.
air will.
It'll get released out like
Okay, what will happen to the balloon? Suppose you just leave the balloon. What will happen to the balloon?
the size shrinks.
Okay, and then what else happens? I mean, you're not holding the balloon anymore. So what happens to the balloon?
It randomly moves around.
It moves around randomly. Okay, it moves in a direction opposite to the direction in which air flows out of it. So something like this will happen. As you said, it moves randomly, correct? So basically, what you observe is something like this. Air will be flowing out of the balloon, and as a result, the balloon will move in the opposite direction. We had discussed this before also in conservation of linear momentum. Right, right. So if you know the rate at which air flows out of the mouth of the balloon, then you can write the rate of flow of momentum. Rate of flow of momentum is nothing but force. Okay, F is equal to dp by dt. You can tell how much force acts on the balloon if you know the rate at which air is flowing out of its mouth. Okay, of course, there are some other things also you need to know, like density of air and all. If you know all those, then based on this dp by dt, rate of flow of linear momentum, you can tell how much force acts on the balloon. And from that, you can find out its acceleration and so on. We'll solve problems like this in this chapter also. We had discussed this in, I mean, we had made use of this idea in rocket propulsion, in laws of motion, okay? Linear momentum conservation or rocket propulsion. We'll be using it in fluids also. Okay. So now you know how to write rate of flow of volume through a cross section, rate of flow of mass, and rate of flow of linear momentum also. Fine. Now consider a tube like this, a tube of varying cross section. Assume the area of cross section at one point is A1, at the other point, at another point in that same tube is A2, and let's say some fluid is flowing through it. Okay. Now we are still dealing with ideal fluids itself. Ideal fluids are incompressible. Could be a liquid, could be a gas, but ideal fluid is incompressible. So suppose there's an ideal fluid flowing through this tube. Let's say the speed of flow here, where the cross section is broad, assume the speed of flow is V1. And where the cross section is narrow, assume the speed of flow is V2. Fine. Now, I'm sure some of you must have, or all of you must have watered plants at some point, or at least played with water flowing out of a tap. Okay. Now, answer this directly. Suppose water is flowing out of a pipe or a tap, and you cover the mouth of the pipe or the tap partially. What happens to the speed of flow of water? If you partially cover the mouth of the pipe or tap, what happens to the speed of flow of water?
It will increase, sir.
It will increase. Correct. Okay. And it increases because of incompressibility of the fluid. Okay. Now see, in real life, when water flows out of a tap or something, water is a real fluid. Real fluids are compressible, but not freely compressible. No, they do offer some resistance. They have some bulk modulus. Their bulk modulus is not zero. Ideal fluid bulk modulus is infinity. Real fluids will have some bulk modulus. Okay, they are not freely compressible. Some uh, resistive force will definitely be there. Okay, so suppose it is an incompressible fluid. Through the cross section A1, if the speed of flow is V1, then you can say the rate at which volume flows into this tube is A1 multiplied with V1. Okay, that's the rate of flow of volume into this part of the pipe. Okay. Then on the other side, where the area of cross section is narrow, the area is A2, speed is V2. Then the rate of flow of volume out of this part of the tube, okay, rate of outflow is A2 V2. Now, if it is an ideal fluid is not allowed to get compressed. It cannot, its density cannot be increased, its density cannot be decreased also. You cannot expand it also. Okay. So a certain amount of ideal fluid has a fixed volume. You can't change its volume. Now this tube is completely filled with liquid, as you can see. As some liquid enters from the left side, some liquid will have to leave on the right side. Okay, let's call it fluid only. Okay, let's not restrict our discussion to liquids. This discussion is applicable to gases also. If it is incompressible, how much ever fluid enters into this section of the tube, the same amount of fluid should leave. Amount means volume. Okay, that means rate of inflow must be equal to rate of outflow if the fluid is incompressible. This equation is called equation of continuity, or this condition is called equation of continuity. Obviously, this is applicable only to ideal fluids. In a real fluid, how to deal and all, you learn in engineering, not now. So if there is one inlet and one outlet, like what you see on screen here, then A1 V1 equal to A2 V2 will be the equation of continuity. Inflow is equal to outflow basically. If there are multiple inlets, multiple outlets, you can say total inflow or total rate of inflow must be equal to total rate of outflow. Okay, basically the volume flowing in per unit time should be equal to the volume flowing out per unit time. That is what is equation of continuity. And if you and to actually write the equation, you need to know how to express volume flow rates. Okay, that is why we had discussed that part first. Okay, let's quickly solve one problem based on this very basic question, but important. Very frequently in exams, questions are asked based on equation of continuity. And this idea of inflow is equal to outflow is applied in some other chapters as well. In fact, after fluids, we'll be dealing with heat and thermodynamics. Okay, there's something called heat flow through conduction. There also we'll be using this idea. Okay, in case of steady state, rate of inflow of heat to any point of the conductor will be equal to rate of outflow. In current electricity also you'll be using this idea. There is a property called conservation of charge. Okay, so charge can neither be created nor be destroyed. So if there is a wire or a junction through which charges are flowing, inflow of charge to that junction should be equal to outflow in a given amount of time. So equation of continuity will be used in, can be written in any case where flow is involved, whether it's fluids or heat or current. Okay, let's solve one problem based on this. Okay. Consider a junction of pipes like this. These are all cylindrical pipes. Fine. Their radii are given as R, 2R, and 3R. Okay, the radii of cross section r, 2r, and 3r. And it is known that liquid flows in from here with a speed v, and liquid flows out from here with a speed 4v. Find out what happens at the third opening, whether it is inflow or outflow, and with what speed. Okay, do this all of you. I'll give you 2 minutes. The fluid is incompressible. You are given the radius of cross section, keep that in mind, and you are given the speeds of flow along with direction at two of the openings of this junction. At the third one, you have to find out what happens. So basically, it's an incompressible fluid. So net rate of inflow or total rate of inflow should be equal to total rate of outflow. Okay. Now, through the third cross section, we don't know whether it is inflow or outflow. You can first find that out if you want. Otherwise, assume something and write the equation. Okay. Assume inflow. Nothing wrong in that. Let's assume inflow with some speed v dash. If it is actually outflow, you'll get a negative answer for v dash. That's all. Okay. So you can write the equations, not an issue. So we are taking inflow in two of the openings and outflow in one of the opening. Now, how do you write equation of continuity? Total rate of inflow should be equal to total rate of outflow. And how do you write rate of inflow or outflow? Area of cross section multiplied with the speed of flow. Therefore, uh, radius is 3r. So area will be pi into 3r whole square. 3r whole square is 9r square. That's the area of cross section multiplied with v. That is one inflow. Plus another inflow, another rate of inflow is pi r square multiplied with v. Okay, v dash. This v dash is what we need to derive. These are the two inflows. Together they should be equal to outflow. Pi into 2r whole square becomes pi into 4r square. And the speed of outflow is 4v. That's all. Pi and r square will get cancelled in all expressions, in all terms. So 9v plus v dash is equal to 16v. So v dash becomes 16 minus 9, 7v. Correct. And we got a positive answer. Okay, what does the positive answer signify? It signifies that the direction we have assumed is correct. Okay, Aishwarya, good. So how many ever inflows, outflows are there, you can manage. Okay. Next, when a fluid actually flows through a pipe, okay, pipe or through some cross section, there are different kinds of flow. Okay, let me just show you one image. 1 second. Okay, consider these examples. Here you see smoke flowing, okay, from incense sticks. Now, if you observe carefully, there is some distance up to which the flow is smooth. Okay. After that, it becomes disturbed, right? So these are basically the two different kinds of flow. Okay. The flow, I mean, the part of the flow which is smooth is called steady flow. Steady, or you can also call it as streamline flow. Fine. And the part where it is disturbed is called turbulent flow. Okay. And basically what happens, see here, streamline turbulence, that shift is happening. No, smoke up to some distance, it is rising smoothly. After that, it is getting disturbed. There are many reasons why that could happen. Air could be flowing around, so the flow can get disturbed. But even if air is not flowing around, based on the speed of flow, it can change from steady flow to turbulent flow. Okay, so these are basically two different kinds of flow. We'll first discuss the properties of streamline flow or steady flow. This will help us in describing the mechanics of moving fluids or flowing fluids. Right. Consider a tube like this through which a fluid is flowing. So this part of the tube is filled with fluid molecules. Okay. Consider one position in this tube. Let's call this position as A. Position means place, location. Now, as the fluid flows through this tube, at a given instant, there will be one fluid particle at this position. Let's say it is some gray colored fluid that is flowing. Okay, it could be smoke, it could be liquid, whatever it is. One fluid particle will be at that position. Okay, and because it is flowing, let's say the flow is in this direction. Because it is flowing, this fluid particle will have some velocity. Let's say it has a velocity VA. Okay, the velocity of the particle which is at position A. The particle's name is not A, the position's name is A. Remember that. Okay, fine. Now you know that as the area of cross section varies, the speed of flow can vary. We had just proved that also in equation of continuity. A1 V1 equal to A2 V2. And you know where the pipe becomes narrow, the speed of flow increases. Okay, like from this equation itself, you can tell A1 V1 equal to A2 V2 means AV is constant. So if A decreases, V increases. So where the pipe becomes narrow, the speed increases, even if it's an ideal fluid, right? So same thing could happen here also. As the fluid flows through this pipe, this particle need not always have the same speed. At this position, it has this speed. Going to some other position, its speed may increase or decrease because the pipe's area of cross section is changing. Okay. So when it goes ahead, let's consider another position, some different position. Let's say this one. Let's call this position as B. So when particle reaches B, its velocity may be different. Okay, depending on the area of cross section and all. What happens to area of cross section and all. Here I have assumed the area of cross section is becoming narrow. Therefore, the speed of the particle has to increase, velocity has to increase. So let's say this is the velocity at position B. It's the same particle, okay, which went from this place to that place. Fine. Now, as the particle goes from A to B, it would follow some path. Okay, there would definitely be some path that it takes. Let's visualize that path also. Maybe somewhat like this. Okay, it moved from A to B. Now, when this particle, the particle that we are considering, is at A, its velocity is VA, then based on that velocity VA, or with that velocity VA, it will shift to the next position. This particle will go forward. If this particle goes forward, some other particle will come and take its place. Okay, the particle which is after it in line will come and take its place because fluid is continuously flowing. Okay. Now comes the definition of steady flow. When fluid is flowing and it flows in such a way that any particle coming to a particular position, okay, for example, any particle coming to A has the same velocity as the previous particle at that position. Means at a given position, velocity is fixed. All the particles that pass through that position will pass with the same velocity. Okay, at a different position, the velocity can be different, but at a given position, all particles passing through that position must pass with the same velocity. That kind of flow is what you call as steady flow. Okay, I'll write the definition here. The velocity of any particle flowing through a particular position is equal to that of the previous particle at that position. Okay, so let's call this particle as X if you want. X will go ahead at the next moment. Some other particle Y will take that place. Y also should have the same velocity which X had when it was there. And that should happen everywhere. Then the flow is called steady flow. Is this clear to all of you? The velocity of flow at a particular position is fixed. Any particle coming to that position must have the same velocity which the previous particle there had. Okay. Now what happens if that property is obeyed? Now see, this particle X has a velocity VA when it is at A. With that velocity, it will go to the next position. Okay. At the next position, for that particular position, there may be some other velocity. With that velocity, it will go to another position, another position, another position, and so on. It will keep moving that way. Now consider another particle Y. When Y comes to this place, Y will have the same velocity that X had. Okay. So what will happen? If it has the same velocity, it will move in the same direction as X. It will move at the same rate as x. So whatever x did, y will also do the same. The next particle following it will also do the same. Okay, that means there will be fixed paths along which the particles will flow. Any particle starting from here has to flow along this path. Similarly, you can take another path also. Let me use a different color. Any particle that starts from this position, suppose one particle went this way along this path, every other particle which starts from there will follow the same path. Why? Because every particle will take the same, what do you say, same velocities along the way. Fine. Which whatever velocity the first particle followed from as it moved from position to position, the same velocity pattern the following particles will also follow. So whatever path one particle follows, every other particle will follow the same path if it started from the same place. Fine. These lines or these curves are called streamlines. So what are streamlines basically? Streamlines are nothing but path or paths of flow of particles in steady flow. There will be infinite such paths, okay, depending on where the particle starts from. So these are what we call streamlines. That's why steady flow is also called streamline flow. They are one and the same. Okay. Now tell me from your understanding of streamline. See, how do we draw the streamline? You trace the path followed by one particle, that becomes a streamline. You trace path followed by another particle, that becomes another streamline. Okay. And every particle starting from a particular position will follow the same streamline. Okay. Now you consider this. Suppose this is one streamline. Okay, let's say there is streamline flow happening somewhere, and this is one streamline, and this is another streamline. The streamlines are crossing each other. Now, how did we draw the streamline in the first place? Basically, we trace the path followed by one of the particles. Okay, let's call this particle as x. X went along this way. So we got a streamline like this. Okay. Consider another particle, call this as y. Y went along this way. So we got another streamline like this. What is wrong in this diagram? Recollect what is streamline flow, what is steady flow. And based on that, you tell me, why is this diagram wrong? I'll give you all 1 minute to think. Okay. See, how do we draw streamlines? We trace the path followed by the particles, right? Suppose you trace the path along which x moves and you find that x moves like this. Now we are calling them streamlines, means the flow is steady flow. What is the meaning of steady flow? Any particle arriving at a particular position must have the same velocity as any other particle which comes to that position. Okay. Suppose x moved along this streamline, this path, and you found that another particle y, or someone says that another particle y moved along this path. What does that mean? That means when x was here, its velocity was in this direction, but when y is here, its velocity is in this direction. Is this possible in steady flow? At a particular position, will two different velocities be possible? In steady flow, is that possible by definition?
Sorry.
No. Okay. Steady flow means at a particular position in the tube or whatever it is, there is a fixed velocity. Any particle coming there must move with the same velocity. Velocity includes direction, no, not just speed. So if you show, or if someone shows two streamlines to be intersecting, then that diagram is definitely wrong. It cannot indicate streamline flow at all. Okay, so remember, streamlines do not intersect. Basically, what it means is it's meaningless to draw streamlines intersecting each other. It doesn't make sense. Fine. So basically, what do streamlines show you? Streamlines show you the path followed by any one particle in steady flow. That is what is streamline, right? And because the flow is steady at a particular position, only one direction of motion is possible. So if you are showing streamlines to be intersecting, it means at a particular position, you are saying two different velocities are possible. Then the flow itself is not steady flow. Then you should not call them streamlines. Okay. So never show streamlines intersecting each other. Okay. As a property, we say streamlines do not intersect. Actually, they should not intersect. Right. So now you know equation of continuity, and you know the basic difference between steady flow and turbulent flow, streamline flow and turbulent flow. For turbulent flow, we have not discussed any properties. Basically, flow which is not streamline is turbulent. Okay, remember it that way. Streamline, you know what is streamline flow now. Fine. Using all these properties, okay, if we apply, keep this point in mind, if we apply work kinetic energy theorem to an ideal fluid in streamline flow or in steady flow, what we get is called Bernoulli's equation. Fine. And based on that equation, we can give a statement. That statement is called Bernoulli's principle. Okay. Let us derive this carefully. This is very important. If you are preparing for JEE Advanced, then the derivation is also very important, not just the equation. Okay. So just give me a minute. I'll draw the diagram. Fine. Consider an ideal fluid in steady flow through a pipe of varying cross section like this. Not just the area of cross section, the height of different parts of the pipe is different from the ground. Okay. Ground, or basically, this is the reference level for gravitational potential energy. If you remember, whenever we calculate gravitational potential energy, we first fix a reference level, and any height above that, the gravitational potential energy is plus mgh. Below that, it is minus mgh. Okay. So let's say that is the reference level for gravitational potential energy. Now, as fluid flows through this pipe, Bernoulli's equation is applicable to liquids as well as gases. Okay, so we'll call it fluid. As fluid flows through this pipe, ideal fluid in steady flow, we consider a section of this fluid, some part of this fluid, and apply work energy theorem to it. Okay, that equation itself is what you call as Bernoulli's equation. So let's consider some part of the fluid first. Assume this part, the part between this cross section and this one. Okay, we are taking a significant volume of the fluid. Fine. Let's say the area of cross section is A1 here and A2 here. Obviously, A2 is narrow compared to A1. And let's say the speed of flow here is V1. Speed of flow here is V2. Okay. We'll have to consider the pipe to be narrow compared to these heights. In this diagram, it doesn't appear that narrow, but compared to these heights, okay, let's call this height as H1 and this height as H2. Compared to them, the thickness, not thickness, I should say, width of the pipe is negligible. Okay. Or the radius or diameter of the pipe is very small compared to these heights. That is what I mean. That assumption is important. You can't apply this to very broad pipes. Fine. And the pressure in the fluid at the area of cross section A1 is P1, and at cross section A2, let's say the pressure is P2. Okay. Now you all tell me, you know that when we close the mouth of a pipe partially, the liquid flows out with a greater speed. Okay. Water flows out with a greater speed. We have experienced that in daily life. Just a moment, let me download one picture showing that also. Right. Consider this image. So as the person has partially closed the mouth of the pipe, you know water flows out of the pipe with a greater velocity. So the velocity of flow here, V2, will be greater than the velocity of flow inside the pipe, V1. Okay, V2 is definitely greater than V1. Okay. Now it's a fluid, it will have some pressure. Let's call the pressure of this fluid, okay, the water that has come out, let's say it is at pressure P2, and the water that is inside the pipe, let's say it is at pressure P1. Now take a guess, which pressure do you think is greater? Pressure of water inside the pipe or outside the pipe, if this is happening? Think for a minute and give your answers, all of you. You can take a guess. Actually, you don't know any equation as of now to calculate these pressures and all. Right? Okay, I got two answers as P2 greater than P1 and one answer as P1 greater than P2. Uh, Pawan, are you able to unmute?
Yes, sir.
Yeah. Why do you think P1 is greater than P2?
సార్ లోపల నుంచి ఎక్కువ ప్రెషర్ తో పుష్ చేశాను కదా సార్, అప్పుడు బయటకి ఎక్కువ ఫోర్స్ చేయలేదు.
Okay. Okay. So because the pressure is more inside, you are saying when it comes out, its speed is higher. Makes sense. Vanilla, why do you think P2 is greater than P1?
Sir, V2 is greater than V1.
V2 is
So,
definitely greater than V1. So why should P2 be more than P1?
sir, P2 మీద atmospheric pressure గా ఉంటుంది అని. ఆ water
Okay. Okay, we'll see. We'll see. But see, as the water is flowing out of the pipe, its speed is increasing. So what Pawan said is correct actually. If you consider the water column like this, some part of water, okay? Pressure here is P2, pressure here is P1. And as it goes this way, speed is increasing, means there is force in that direction. Now due to P1, there will be a force force this way. Due to P2, there will be a force this way. Now it is accelerating to the left. Okay, its speed is increasing to the left, means what? It is accelerating to the left. If it is accelerating to the left, there must be more force to the left than to the right. Means force due to P1 must be more than force due to P2. Only then it can speed up, no? So pressure P1 is more than pressure P2. Okay, that is correct actually. Inside the pipe, pressure will be more. As it comes out, pressure is released. That's why it becomes faster. Okay, or you can say due to that pressure variation only, it gains that extra speed. We will now prove it mathematically. Okay, by using Bernoulli's equation. Fine. So consider this. I'll have to remove all this. Just a moment. Yeah, consider this situation: ideal fluid undergoing steady flow through a pipe of varying cross section and varying height. So we have considered some part of this fluid, right? And the part of the fluid we considered now is between, let's just name these points. Let's say it is between A, B. Okay, AB is one cross section. CD. CD is another cross section. Okay. Now in some time, in a small amount of time, this part of the fluid will move forward. Now here you clearly know that V2 is more than V1. Where the cross-sectional area is narrow, the speed will be greater. So in some time, if you visualize these cross sections moving forward, let's say AB cross section moves to this position. It has moved some distance. How much distance it has moved? Speed into time, V1 into dt. Okay. That CD cross section also will move some distance ahead, but CD is moving faster than AB. So it will cover a greater distance. Let's say it goes all the way till here in a small time dt only. So how much distance will that cover? V2 dt. Actually, these are supposed to be very small, but for our visualization, I'm showing significant distances here. So the fluid was initially between AB and CD. Finally, where is it? It has like the area, the cross sections have moved forward. So let's say it is finally between PQ and RS. Okay, I'll mark them in red. AB shifts to PQ, CD shifts to RS. Okay, so the whatever liquid was or whatever fluid was between AB, CD is finally between PQ, RS. During this displacement, we need to write work kinetic energy theorem for that part of the fluid. Can one of you quickly tell me work kinetic energy theorem?
so work done equal to change in kinetic energy.
Correct. Uh, Almost correct. Work done by all forces acting on the system. And by all, we mean internal as well as external. Okay, we had discussed in that chapter that internal forces also can do work. Work done by all forces on a system is equal to the change in kinetic energy. Now, what is the system that we are considering here? The system is the part of the liquid. Okay, let me uh, show it separately. Let's consider the part of the liquid between AB and CD itself. Okay, it has a boundary also. This part of the liquid is what we are interested in or what we are applying the equation to. So let's treat this as an object now. Now, as this part of the liquid fluid flows through the pipe, we need to apply work kinetic energy theorem. Means we have to first identify what all forces act on it, which forces do work on it. Okay. So one of you tell me, as the fluid flows through the pipe, what all forces act on it? What are some basic forces that we consider? Always.
Gravitational force.
Gravity will definitely be acting. That is one of the forces, correct? Next. Okay. If you make a hole in this pipe, fluid will leak out. What does that mean? Before leaking out, the fluid would have been pushing the walls of the container, walls of the pipe. And the walls of the pipe would be pushing the fluid also. Okay. So gravitational force is one force that is acting. And there will be normal force acting on the fluid from the walls of the pipe. Like this. They are kind of keeping the fluid confined to that volume, to that space. They are not allowing it to leak out. Okay. So that normal force from the walls of the pipe will be there. Okay. Now fluid is flowing parallel to the wall of the pipe. Now when one material moves parallel to another material or slides on another material, friction can act. But what kind of a fluid have we considered? Ideal fluid. Ideal fluids are non-viscous. Non-viscous. Viscosity means what? Friction between fluid layers. Okay. So if it's an ideal fluid, there is no friction between the fluid and the walls of the pipe. So remember, whatever we are going to derive from now onwards is based on the fact that it's an ideal fluid. So there's no friction, there's no work done by friction also, need not consider it. Next, due to pressure, okay, the pressure at one end is P1. Due to that pressure, there will be one force acting like this. How much is that? P1A1, pressure multiplied with area of cross section. And at the other end, the pressure is P2. Due to that pressure, there will be a force acting like this, P2A2. We are looking at forces acting on this part of the fluid. The surrounding fluid will exert, no? So from one side, the force is P1A1, the other side, force is P2A2. So resultant of these two will be P1A1 minus P2A2. Or, okay, we are just naming the forces. You can call it as force due to the surrounding fluid. Force due to pressure of the surrounding fluid. Okay. That's all. These are the forces that act on the fluid as it flows through the pipe. Normal force from the walls we have considered. Basically, this pressure into area is nothing but normal force from the surrounding fluid. That part we have considered. Gravity we have considered. Tension, spring force, such other forces are not going to act anywhere. You don't have to apply any pseudo force. We are looking at it from the ground reference frame. Fine. So work done by gravity plus work done by the normal force exerted by the walls of the pipe plus work done by the surrounding fluid. All these should together be equal to change in kinetic energy of that part of the fluid. Fine. Now we'll have to write expressions for each of these. Now you all think carefully and tell me, will any of these be zero? Will the work done by any of these forces be zero? I'll give you a minute, think about it. Okay, you visualize the flow and think carefully if the work done by any of these forces will be zero. Do you think the work done by any of these forces will be zero? See, all these forces are definitely acting. Force which are not acting, we have not considered. Friction and all we didn't consider. Yeah, Vanilla, you were going to say something.
So then force.
Work done by the normal force. Can you justify why is this zero?
So the normal force is perpendicular to the
Correct. The particles move parallel to the wall of the tube, wall of the pipe. Okay. But the normal force acts perpendicular to the wall of the pipe. Since the force is perpendicular to displacement, work done by that force should definitely be zero. The other two forces, gravity and force exerted by the surrounding fluid, you cannot guarantee that the work done by them will be zero. Okay, so we need to write expressions for those two and equate it to the change in kinetic energy. Okay, follow me carefully, all of you. First, work done by gravity. Gravity is a conservative force. Okay. And work done by conservative force can also be calculated as negative of change in potential energy. Okay. Change is final minus initial. Negative of change will be initial minus final. Okay. Whose potential energy? The part of the fluid that we are considering. Which is the part of the fluid that we are considering? The part between AB and CD. After undergoing some displacement, you will find it between PQ and RS. Okay. So basically, if you want initial potential energy minus final potential energy of that part of the fluid, what you need to do is potential energy when it is between AB and CD minus potential energy when it is between PQ and RS. Okay. But you can see that when the fluid is between AB and CD and when it is between PQ and RS, there is some part which is common, PQCD. This is common to initial and final parts that we consider, okay, or positions that we consider. We can take advantage of that. So potential energy when it is between AB and CD can be written as potential energy between AB, PQ, okay. ABCD can be written as AB, PQ, and then PQCD. That is what I'm doing. Potential energy of the fluid between PQCD minus potential energy of the fluid between PQ and RS can be written as fluid between PQ and CD plus fluid between CD and RS. So potential energy of the fluid between PQ and CD plus potential energy of the fluid between CD and RS. Okay. Now you see that there are two terms common here. Potential energy of the fluid between PQ and CD. But this is from the initial situation and this is from the final situation, right? Initially, some fluid particles would have been present between PQ and CD. They will go forward and some other particles will come and take their place. So the particles which were present here initially and the particles which are present here finally are not the same. Particles will go forward, they'll get replaced by some other particles. So is there a guarantee that the potential energy stored in that space initially and finally is same? There is a guarantee. When will potential energy be same? If the mass is same, the potential energy will be same. Okay. Like I'll repeat, what I'm actually asking you is, or what we are actually discussing about is the potential energy of this part of the fluid. Initially and finally, will it be same? Okay. If the mass present here initially and finally is same, if the mass distribution is same, then the potential energy has to be same. And what is the guarantee that the mass distribution will be same? The fact that it is an ideal fluid. How much ever mass was present in that space, PQCD, initially, later also, when some new particles come there also, the same amount of mass will be present between PQ and CD. Okay. Therefore, the initial potential energy in that space will be equal to the final potential energy in that space. Then they can be cancelled. So the total change in potential energy, not change actually, negative of change in potential energy will be potential energy in the space ABPQ minus potential energy of fluid in the space CDRS. Okay. Potential energy is mgh. So we need to know how much mass is there in this space and how much mass is there in this space. Okay. Mass is density into volume. ABPQ, how do you write the volume? Area of cross section multiplied with the distance. Area of cross section is A1. Distance is V1 dt. Their product is the volume ABPQ. And density multiplied with volume will give you the mass. Therefore, potential energy in the region ABPQ will be density into volume. Volume is area of cross section multiplied with the length of that column. Okay. This is mass into G into H1. Why? Because the height of that cross section was H1 from the ground. Okay. As I said, the distance between AB and PQ is very small. For us to be able to visualize, I have shown it significantly large. In small time, it will shift only small distance. No? So AB, PQ are almost at the same height from the ground. That height is H1 minus potential energy in the region CDRS. Again, mgh, how much mass will be present there? Density into volume there. Volume of CDRS is area of cross section A2 multiplied with the length of that column V2 dt. Okay. So density into volume A2 V2 dt, that is mass, into G into H2 becomes the potential energy there. Therefore, this is the work done by gravity. This is the expression for work done by gravity. Okay. Put this aside. Next, we need to write an expression for work done by the surrounding fluid. Now, the fluid that we have considered is moving ahead, moving to the right. Okay. If it is moving to the right, basically what will happen? The pressure P1, whatever force it creates, does a positive work. And pressure P2, whatever force it creates, will do a negative work. P1 is acting in the direction of flow, not P1, sorry. The force due to P1 is acting in the direction of flow. The force due to P2 is acting opposite to the direction of flow. Fine. Therefore, one will do positive work, the other will do negative work. How much positive and how much negative work? We have to write expressions for it. Second, work done by surrounding fluid. Force from one side is P1A1 and the displacement of that cross section is V1 dt. Therefore, the work done becomes P1A1 V1 dt. Force from the other side is P2A2 and the displacement of cross section there is V2 dt. And why did we put a minus sign? Because these forces are in opposite directions, but displacements are in the same directions. One does positive work, the other does negative work. So total work done is this much. This is the second equation. Okay. We have to equate this sum to the change in kinetic energy. Observe this carefully. Change in kinetic energy is basically final kinetic energy minus initial kinetic energy. That means final kinetic energy, finally it is between PQ and RS, no? So kinetic energy of the liquid fluid present between PQ RS minus kinetic energy of the fluid present between ABCD. Okay. Now PQRS ABCD have something in common. You can split this as kinetic energy between PQCD. That is what PQRS was, no? PQCD plus CDRS. So kinetic energy in this space plus the kinetic energy in this space, CDRS, minus of ABCD. Also, we can split it into two parts. Kinetic energy between AB and PQ plus kinetic energy in the space between PQ and CD. Okay. Again, in these two terms, kinetic energy in the space between PQ, CD appears to be common. But this is initial kinetic energy in that space, and this is final kinetic energy in that space. Let us verify if the kinetic energy on that space initially and finally will be same or not. Okay, go back to the diagram. Observe the space PQCD. Initially, some particles will be present there. As the fluid moves forward, some new particles will take that place. Initially, whatever particles were present, due to their masses and velocities, there would have been some kinetic energy. Now, those particles will move forward. New particles will come and take their places. Now, we have assumed steady flow. What does steady flow mean? Any particle coming to a particular place will have the same velocity as the previous particle at that place. Okay. So if you visualize some places here, let's say like this. Initially, one set of particles will be at these places. They'll have one profile of velocities. After some time, new particles will come to these places, but they will have the same velocities which the previous set of particles had. Therefore, the kinetic energy in that space initially and finally will be the same. This is why it is important that the flow is steady flow. Otherwise, you can't cancel those terms. Okay. This is why Bernoulli's equation is applicable only to ideal fluids and steady flow. Mass distribution should be same. Velocity distribution also should be same in that space. Only then you will get Bernoulli's equation properly. Okay. So this is where the assumptions matter. So since we have assumed ideal fluid in steady flow, this term and this term can be cancelled safely. Okay. Now, what are we left with? Kinetic energy in the region CDRS. Kinetic energy is half mv square. So half into CDRS is that last part, no? Density into volume is A2 V2 dt. So half into mass into V square. So V2 square. Minus kinetic energy in the region ABPQ. Half into mass. Density into volume. Volume is A1 V1 dt. Multiplied with square of speed V1 square. Okay, this side the fluid is moving with speed V1, there it is moving with speed V2. So this is the expression for change in kinetic energy, third part of the equation. So we got work done by the forces, gravity and surrounding fluid, and we got expression for change in kinetic energy. Put them all together, what you get is Bernoulli's equation. Okay, so I just copy paste these equations. Work done by gravity plus work done by the surrounding fluid. Surrounding fluid work done is this much. Simple expression. Together, these should be equal to change in kinetic energy. Change in kinetic energy expression is this. Okay, let me write it this way. Okay. Now, in all these terms, if you observe, dt will be common. It can be cancelled. Okay, on both sides of the equation, you have dt. After simplification, it becomes a very easy equation. And we have considered ideal fluid. Ideal fluid is incompressible. Ideal fluid should obey equation of continuity. Now, in this case, how do you write equation of continuity? A1 V1, the rate of flow at the first cross section, should be equal to A2 V2, the rate of flow at the other cross section. Inflow should be equal to outflow. So A1 V1, A2 V2 are equal. And you see that those terms are present in all these terms. Okay. So A1 V1, A2 V2, A1 V1, A2 V2, A2 V2, A1 V1. They are common, they are equal, they'll get cancelled. What will you be left with? Rho G H1 minus rho G H2. That is what you'll be left with from the first part, work done by gravity. Next, P1 minus P2. That you'll get from the second part of the equation. Then the right hand side of the equation, half rho V2 square minus half rho V1 square. See, this you'll find in any book. But what I actually wanted you to understand in this derivation is how the assumptions matter and why the final equation won't be applicable if the assumptions are not satisfied. Ideal fluid and steady flow. Okay, fine. Now keep all the 1 terms on one side and 2 terms on the other side. You get rho G H1 plus half rho V1 square plus P1 is equal to P2 plus rho G H2 plus half rho V2 square. Now remember, H in Bernoulli's equation is height from the reference level. Earlier, when we wrote P naught plus rho G H, actually we should have written it as P naught plus rho G Y to avoid confusion. But anyway, in static fluid, we derived the expression for pressure at a depth H. There H was depth. But in Bernoulli's equation, H is the height from the reference level. Keep this point in mind. Okay, so look at the terms that you see on the left-hand side. P1, rho G H1, half rho V1 square. Right-hand side also you have similar terms, but at another position, that's all. So the entire left-hand side is the sum of 3 terms taken at one place. Right-hand side is the sum of 3 terms taken at another place in the same fluid. Okay, in the same flowing fluid. So basically you can write the equation like this. Therefore, the sum of pressure plus rho GH plus half rho V square will be uniform. Okay, most books write this as constant. Forget the term constant. It has to be uniform. What does uniform mean? Same at every place at a given moment. This is what is Bernoulli's equation. This sum should be the same everywhere in the fluid. And when does this happen? When the fluid is ideal and it is undergoing steady flow, this will happen. Okay, P plus rho GH plus half rho V square is uniform. Okay, hope the derivation is clear. Next class, we'll discuss the applications of Bernoulli's equation. Very, very important part of your syllabus for final exam, from final exam point of view. Okay, fine. Thank you all. We'll continue in the next class.